Hello everyone, let's continue the chapter 8 part 2, synchronous counter. On the previous video, uh, we covered on the asynchronous counter, but now for this part 2 video, synchronous counter. A synchronous counter is one in which the flip-flop within the counter are clocked at the same time by a common clock pulse. Synchronous counters overcome the disadvantage of accumulated propagation delays, but generally they require more circuitry to control state change. Okay, similar to asynchronous counter, synchronous counter also can be designed using PET and ET. However, the connection for synchronous counter is the same whether it is designed using PET or NET. Nevertheless, the connection between a 3-bit counter, 4-bit counter, 5-bit counter, and so on are different from each other. So let's have a look at the first 2-bit synchronous counter. Both are similar, only that for PET JK flip-flop, the counting will trigger on positive edge clock, while for negative JK flip-flop on the negative edge clock. So output from the first flip-flop will be the input for the next flip-flop. So this is the circuit of the 2-bit synchronous counter. So if you look at this circuit or the connection of the flip-flop properly, you can differentiate between the synchronous and asynchronous counter. So the synchronous counter, if you look at the clock here, it is connected to one source of clock. This is clock for the first JK flip-flop. This is clock for the second JK flip-flop. So if we use, this is the positive trigger. How do we know this is positive clock? Because there is no bubble here, and this is the negative edge trigger JK flip-flop because we have the bubble here. So if we look at the waveform carefully, it overcome the problem of propagation delay. So this is the timing diagram that explain the propagation delay of asynchronous and synchronous. Okay, propagation delay through flip-flop 0, flip-flop 1, flip-flop 0, and flip-flop 1. So it has the propagation delay if we look at the timing diagram. The 3-bit synchronous counter, for a 3-bit synchronous counter, the output of the first and second flip-flop are AND together. And its output is fed as input for the third flip-flop. So this is the 3-bit synchronous counter. The purpose of the addition of AND gate is to delay the toggle action involved in the second flip-flop and so on. This will be discussed more in details later on the next slide. So this is the 3-bit synchronous counter. For the circuit, we will discuss detail on the next slide, but this is the example of a 3-bit synchronous counter. We have an AND gate between the flip-flop second and third flip-flop. So let's look at the waveform or the timing diagram so that we can understand the operational of the 3-bit synchronous counter. Notice that the output waveform is similar to a synchronous counter. This is because the purpose of any counter is to produce waveform in counting sequence. The waveform is same because it is counting, right? But only the difference is the configuration of the circuit, the connection to the clock that is different, and it has some advantages between the synchronous and asynchronous clock. So if you look at the waveform carefully and try to understand how we get the Q0, Q1, and Q2. So if you look at the clock, if so this is considered positive lah. Let's say this is the example of a positive trigger, PGT, PET, positive H trigger. Okay. This is positive here, right? Clock here. Clock here. Okay. So let's see the first clock here. So what is the output of Q0? Let's see that this is the output of Q0, the first positive clock. Let's say this JK means that connected to 5 volt. 5 volt means that logic 1. Both of the input of JK is 1, 1. So it is toggle. So what is the Q0? So Q0 will toggle from the previous state. This is first toggle 0 kan. First, then Q1 also will get the output at the same time. Q1. This is a Q1. Q0, Q1. Output at the same time. Q1. Okay, Q1. Because why? Because this flip-flop is depending on the same clock. So you can see the different from previous asynchronous counter. So once there is a clock, so automatically these three output will getting the output at the same time, kan? Without need to wait the output from first flip flop to become the clock for the next flip flop. Okay, that's why you see ada satu je clock, so semua dapat output trigger tu kosong semua kan. So next tengok next. So next clock Q0. This is Q0. Q0 next clock Q0 will have the output dekat sini. What is the output? What is the input of JK? Input of JK still 1, 1. So it's toggle. Toggle means that if the previous 0, so it toggle to 1. Kat sini pula ada clock. What is the input JK? Input JK is coming from this Q. Tengok ni Q. So Q sebelum tu adalah kosong. Ni kan, ni kosong. What is the K? Sama juga. So sini kosong. So output Q, no change. That's why you see the second one, no change. Here is also same. Look at this connection. Then you can fit all the logic gate into all the logic into all the flip-flop or gates here to get the output sampai habis. Then you get this waveform. If you look at the counter, it's counting 0, 0, 0 kan, 0, 0, 1, 0, 1, 0, 0, 1, 1, so on and so forth. Okay, the next slide shows how to analyze this counter by writing the logic equation for each input. Notice the inputs to each flip-flop. Analysis of synchronous counter. A tabular techniques for analysis is illustrated for the counter on the previous slide. Start by setting up the output as shown, then write the logic equation for each input. This has been done for the counter. Output, first put the counter in an arbitrary state, then determine the inputs for this state. Okay, outputs 0, 0, 0, logic for input, J2, Q0, Q1, J2 equals to Q0, Q1, J2. Where is J2? Here is J2. Okay, Q, J2, Q0, Q1. K2, Q0, Q1, J1, Q0, J1 is coming from Q0. Okay, and K1 from Q0, J0 and Q0, Q0, 1, K0 equals to 1. Okay, then we put 0, 0, 0, J2, J2, Q2, 0, 0, 1, 1. Use the new inputs to determine the next state. Q2 and Q1 will latch and Q0 will toggle. 0, 0, 1. Okay, set up the next group of inputs from the current output. So what is the input? What is the input for the output of 0, 0, 1? J2, K2 equals to 0, 0. J1, K1 equals to 1, 1. J0, K0 equals to 1, 1. Okay. And number 4, Q2 will latch again, but both Q1 and Q0 will toggle. Continue like this to complete the table. The next slide shows the complete table. Okay. If you look at the output 0, 0, 0, J2, K2, 0, 0, J1, K1, 0, 0, J0, J1, K1, 0, 0, J0, K0, 1, 1. For the output 0, 0, 1, 0, 0, 1, J2, K2, J2, K2, 0, 0, J1, K1, 1, 1, which is a toggle, right? J0, K0 is toggle 0 to 1. So on and so forth. At this point, all states have been counted for, and the counter is ready to recycle. So this is the analysis of synchronous counter. So next, 4 bit synchronous counter. 4 bits asynchronous counter can be designed by following the trend of ending the output from the previous flip-flop and flip-flop before that. Similarly to asynchronous decade counter, synchronous decade counter can be designed by adding NAND gate to reset all flip-flop when the counting reach the number 1, 0. So this is the asynchronous counter. Beside from decade counter, it can also be modified to count up to a certain number. For an example, modulus 12 synchronous counter can be designed as like this. Okay, synchronous decade counter. It is similar to asynchronous counter, but only the difference is the connection or circuit. So this is the IC 74163 4-bit asynchronous binary counter with additional features over a basic counter. So this is the IC for the synchronous binary counter. This is the timing diagram. 4-bit synchronous BCD decade counter. So this is a timing diagram. up-down synchronous counters. An up-down counter is capable of progressing in either direction depending on control input. So this is the uh, up-down control synchronous counter. Okay, example up, down, up, down, up, down. Clock pulse. 0, 1, 2, 3, 4, 5, 6, 7. So up 0, 0, 1, 0, 0, 0, 1, 0, 1, 1, 1. Kemudian down balik 1, 1, 1, 1, 1, 1, 1, 0, 1, 0, 1 until 0, 0, 0. Okay, so this is the up down timing diagram of up down counter. So this is the IC 74HC109 is a high-speed CMOS synchronous up-down decade counter. Okay, this is a block diagram of a 12-hour digital clock. Okay, so that is about the counter, but I will continue on a design of the a counter on the next video. So that's all for this part of the video. See you on the next video. Thank you very much. See you again. Bye-bye.